Now we will look at still on equipment check for how to check the resolution and sensitivity of a UT machine. For resolution, we make use of the one block. We make use of this notch to check for resolution. By definition, what is resolution? The ability of your unit to differentiate between defects that are close together. So if I have, this is a block, and I have, let's say, a defect here, and I have one here, let's say 3 here, and I have, say, another one here. Let's say I have another 2 that are here. Let's assume that these are all side holes, and we are trying to see if our probe, these are 0-degree probe, has the ability to see so this one goes for this goes for this goes for this, and this comes for this. This first one is what we call the near surface resolution. This other one is what we call the far surface resolution. Why do we call it near surface? It's close to the surface of the material where you have the probe. What does the resolution of this mean? If I have an indication or a defect that is very close to the surface of the probe, will the probe be able to clearly differentiate between that initial band and this indication that is here? That is near surface resolution. This one is a far surface, it is a normal resolution, which we call is resolution within the space of the material, inside of the material. Normally we call that spatial resolution. We call it spatial resolution. This is better explained when we are looking at the angle probe, in case we have an angle probe that is sweeping this way. This one is, now when you now talk about, just to get more picture to it, under spatial resolution you have what we call axial resolution, which means if I have my probe going this direction, so I have my beam spreading like this. So this is the axis of the movement of the ultrasound. So 2 indications that are within the axis of this spread. If the probe is able to, or the machine is able to differentiate them, it has what we call the good axial resolution. Then we also have what we call the lateral resolution. They both form part of the spatial resolution. In that case, we're talking about direction, lateral direction. So even though these defects are not aligned to the axis of this probe, but laterally can the probes differentiate between them. So that is your lateral resolution. Why axial resolution is if the indication we are trying to differentiate are within along the axis of the spread of the beam. So this is just a general overview of when you look at different kind of resolutions. But when we check for resolution as an equipment check process, we are just trying to see if the probe, together with the equipment in the setup, is able to differentiate between such indications. So for our 0-degree probe, we have this. We know that this distance, so if I draw it on the board, so this is what we have down here. So we have one distance here, we have another distance here, and we have a third distance here. So if I have a probe, I just purposely I spread it out. But if you look at the way they are here, they are quite close. Looking at them with the probe. So which means this the circumference of the probe is able to capture these three areas. But they are they look like they are far, yeah, they are not far. So this distance from here to here is 100. This is 85. This is 91. So if my equipment is properly calibrated and I put the probe in, I should be able to see clearly three indications. If you look at this, you will see 385. This second one should be 91 and this third one should be 100. If these indications are clearly captured, it means that the resolution of your probe together with your unit, it is okay. So that is just a very short way of getting your resolution. The question is it now near surface resolution? Is it now axial resolution? Now for near surface resolution, you can look for, we can use something like this or any other block where you have a side drill hole that is very close to the surface. You can find them in some of these assessment blocks where you have an indication that is very close to the surface and you put the probe. If the probe is able to differentiate between the front surface and that indication, it means that the near surface resolution is okay. The same also goes for the far surface or the back surface or the backward resolution. If he's able to differentiate clearly between this hole and the backward, it means that the far surface resolution is very, very okay. So that is just a shortcut. It's not shortcut, but that is just a way of determining the resolution, if the resolution is okay. So just the recap, resolution, the ability of the UT equipment to differentiate between defects that are close together. But sensitivity, on the other hand, it is the smallest defect that the machine can detect. So if I have a small hole like this and I have a big hole like this, a machine that has good sensitivity means it can easily see this hole, which means the higher the sensitivity of the machine, the smaller the hole it can get. So that brings us to the conversation of how do we determine the sensitivity of a UT machine. Now, this is a little bit different than the resolution. For sensitivity, you can do that with calculation and verify with your machine. Theoretically, we know that the smallest indication that a UT probe and even a machine setup can get is usually signified as the wavelength divided by 2. So how does this affect the sensitivity? If you look at these two probes, we'll see that this one is 4 megahertz and this one is 2 megahertz. This one is 2 megahertz. This is 4 megahertz. Their sensitivity will not be the same. Normally, we know that the higher the frequency goes up, sensitivity goes up. So, which means a 4 megahertz probe will be more sensitive than a 2 megahertz probe. So, how do you now put that into a practical application? Your sensitivity will be determined. That sensitivity will now determine which size of side drill hole or which size of hole you are going to use when you are doing your calibration. If it is a project you are doing or you have a specific procedure that tells you that use a particular size of hole, you don't have to stress yourself trying to determine the sensitivity on your own. Just follow the procedure. If you are using an ASME related procedure, or you are using a project procedure or an ISO related procedure, where the sensitivity is not expressly stated, it is now up to you to determine it based on one, the kind of probe you are using, and also your UT machine. This you have to verify. So the normally available sizes of O for all the blocks you are going to see that are commercially available, you have your 1.5 mm, your 3 mm, and you have your 5 mm. Obviously, if you calibrate with 1.5 mm, this has the highest sensitivity and this has the lowest sensitivity. So how do you determine which sensitivity you are going to use? That is where this formula comes in. We already know that the smallest defect that any probe can catch determines the sensitivity. So if I have a 2 megahertz probe, 2 megahertz, and I'm going to work on a steel material, carbon steel material, we know that velocity V is F lambda, which means lambda becomes velocity over F. We already know the velocity for steel, normally, which will be 5920 meter per second, and your frequency for this one is 2 megahertz, which is 2 times 10 to the power 6. So that will give you 0.00296 meter, which is 2.96 millimeter. What does this mean? It means that if I am using my 2 megahertz probe, the smallest defect I can get, take note, this is the wavelength that I've calculated. The smallest defect will be 2.92 all over 2, which is 1.46 mm. Which means any O below 1.4 megahertz has this to do your sensitivity, to check for your sensitivity. So the same principle applies if I'm using my 4 megahertz. If I'm using my 4 megahertz, it's just to put this value of 4 in, and I'm sure this value is also going to change. And if you check that, we are going to be getting even a much lower value because this has a higher sensitivity. So from what this is telling us from the calculation, for both 4 megahertz and 2 megahertz, 2 megahertz and 4 megahertz, we can use any of these holes to do our sensitivity. But if I have maybe 1 megahertz, obviously if you check from this calculation, you are not going to be able to use your 1.5 mm side rule to do your sensitivity. So basically, how do you check sensitivity? So if I have my side hole now, this is my side hole, and I put the probe. If I'm able to catch this hole, if I'm able to catch this hole that is here, it means that my sensitivity, it means that my probe sensitivity is okay. So it's just for us to check the depth of, looking at this equipment now, the question you should ask yourself is which is the real one? Is it this echo or this echo? So if you measure the depth of this and you measure the depth of the indications that you are getting, if you are able to get any of them, it means that your sensitivity is okay because this is a 1.5 mm side drill hole. That way you are able to determine your sensitivity. But theoretically, you need to do your calculation to be able to determine what is the smallest size of defect that your probe working in conjunction with your machine can get. Now, you can do this calculation that your probe is able to get 1.46. But the question you should ask yourself is, if you connect it to the equipment, will it be able to determine it? That is why after will it be able to, if you connect to your equipment, will it be able to catch the defect and clearly identify it? That is why after doing your calculation, you still need to test it and see if he's able to get that size of hole that you are showing. But The long and short of it is refer to your procedure, refer to your standard to know the right sensitivity you are going to use. Before you do your test, you now do what you call your sensitivity calibration. That is a scope for, that is a topic, rather, is a topic for a different video, resolution calibration. I hope that helps. Thank you.